nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Lecture 2, and Lecture 2 is a continuation of the discussion about crystals and periodic lattices. As you remember that I mentioned that the materials of interest in the semiconductor industry do not only include crystalline material. There are amorphous material, polysilicon material, of course, liquid crystals that may or may not have the periodic symmetry. But when they do have periodic symmetry, in that case, then a solution of a whole sets of problems becomes particularly easy, and those conclusions that we get from crystalline silicon or crystalline material, we can translate back to amorphous material, polycrystalline material, and others. So we are solving an easy problem in some way so that we can have a broader understanding of how all the materials that is of interest in semiconductor, how they work. Now, let me start by a discussion about the volume and surface issues, about body-centered cubic and face-centered cubic and cubic lattices. That's where we'll start up the discussion today. Now, one thing I want to point out that in the bottom of the slide, you will see the reference, of course, for the book, the page number I'm approximately covering. But at the same time, there are a set of software that you can find in nanohub.org. Presumably, you have had a account there already. You should be using this tool in order to get a better feeling about the various discussions here. Many of the pictures are three-dimensional, and I can only take a snapshot from a particular angle. Things may not be as clear. But in the NanoHub, you may be able to rotate the crystals around so that you get an exact idea where the various atoms are, and that will clarify the concepts. Now, if you remember our discussion so far, that we are interested in calculating current through a semiconductor. And in order to calculate the current, we are interested in the resistivity that depends on the material, as well as the arrangement of the atoms. Now, in that case, we really want to know two quantities. One is this electron density, and which is how many carriers do you have, free carriers you have available for conduction. Different material will have different number. And the other one is velocity, that how fast they move in response to an electric field, for example, or a density gradient. And in order to do that, we want to understand the periodicity of the atoms and the structure of the atoms. And that's why we are trying to understand the symmetry, the number of atoms per centimeter cube for a particular material, and all sorts of basic information. So that if I tell you that in 1 centimeter cube of silicon, how many electrons do you have? You'll be able to say, okay, let me see first, how many atoms do I have to begin with? And per atom, let's see how many electrons I have. And thereby, you might be able to estimate how many electrons you have. So that is what we are after today. And presumably, after this discussion, you'll be able to make that count. Now, if you remember that in the last class, I told you about Bravais lattices. In 1D, there is one type. In 2D, there are 5 types of Bravais lattices. And in 3D, there are 14 types. And 14 types I mentioned the other day are, of course, there is the 7 symmetry. Based on the symmetry group, there are 7 types. And also depending on where the atoms sit, whether in the corner, whether in the body center, or whether in the face center, or on one side or the other of the face, which is the bottom line, then we can sort of categorize these various crystal lattices. And that discussion we had. Now, one very interesting thing is that although there are practical examples of all these crystals, if you go to a natural history museum, you'll be able to find actually examples of all these crystals of various sort. But 70 to 75% of all material actually occur in these three groups. One is this cubic, body-centered cubic and face-centered cubic, and as well as the last one is the hexagonal. And I'll explain these three primarily because the semiconductors of interest, silicon, germanium, silicon carbide, for example, these mostly occur in this cubic, body-centered cubic and face-centered cubic, and as well as hexagonal structures. So we'll spend some time. Now, one example I want to very quickly tell you about, that the cubic, the simplest one on the right-hand side on the top, that one, for many years, there is only one known example, and I think it still is, and that is only one, and that is polonium-84. It's a very strange material, and the way other materials sort of work, this material is so strange, and that only very recently people are understanding how the crystal lattices work for a cubic lattice. It's a very exceptional material, but most other will simply be face-centered cubic, body-centered cubic, and hexagonal. So let's start with cubic lattices. Remember, there's nothing practically here except polonium-84. But let's nonetheless discuss the certain number of concepts. For example, in terms of volume issues, if you wanted to know how many atoms do you have per centimeter cube, then what you could do, you could say that, well, let me take a unit cell, the unit cell of size A, and I construct a unit cell. How many atoms do I have inside the unit cell? Well, one thing you could say 8, right? There are 8 corners. There you could say 8, but of course that will not be a correct answer, because you realize that every corner of that sphere, of that atom, is being shared by 8 neighbors, right? It's a 3D. In 2D there have been 4 neighbors, but in 3D there are 8 neighbors. So what you really get inside your box is 1/8 of the atom. And since you have 1/8 and you have 8 corners, so how many atoms? You have about 1 atom per unit box. And so the number of unit cells, 1/8 points per corner, 8 corners, so it's 1 point per cell. Remember, these are geometrical points. Inside it, there may be many atoms. Remember the basis idea, that this is a geometrical point and the basis may contain multiple atoms inside it. Now from this, if you know the dimension A, you could easily say how many per centimeter cube, right? And from that, you could say how many atoms per centimeter cube for cubic lattices. Now, one thing you realize, and you should convince yourself that although I have done it here in terms of primitive cells, even if my cell were bigger, you see, that shouldn't matter, because then it will contain more atoms, but of course the density cannot change depending on how you mentally partition it up in terms of blocks. And this would be important also for your homework. You'll see that if you use this definition, the density is independent of the definition of the cell, then that will allow you to make some calculations very easily. Now, in terms of cubic lattices, if you wanted to know what fraction of the volume is actually occupied, we just counted number, but what fraction of the volume is occupied, you will see that it is approximately 50%, 52, 53%. And this is how it comes about. You realize that if the two sides, if the lattice spacing is A, then the maximum size an atom can be, a spherical atom can be, the radius of it is A/2. Because A/2 is at that point where the two spheres touch each other. It cannot be bigger than this, because then the electron cloud from one has to penetrate the electron cloud from the other one. And that it cannot do. So it cannot go beyond A/2. So the radius of the sphere is A/2. And so if you wanted to know what fraction of the volume is occupied, then again you will start with, you'd see the second line, 1/8. This is 1/8 from each sphere, 4/3 pi r cube. You know this formula, right? Volume of a sphere. multiplied by 8 corners. So that gives you this 8 corners from the cube divided by a cube. A cube is the volume, total volume. And the result is pi over 6. And pi over 6 is approximately 50%. So 50% of the volume is occupied. And where did the other 50% go? You see there are empty spaces inside this, outside the sphere. That's why the other 50% has gone. One of the strange thing about materials that even if you didn't put things in terms of periodic structure, if you just packed it randomly, still the answer will be very close to 52%. It's a constant that you find over and over again, not only in periodic crystals, but also in all sorts of amorphous materials, about 54, 56%, even for random packing. Okay, cubic lattice. What about surface issues? That if I wanted to know not only volume, but let's say I have a semiconductor that's terminated by a surface, and I'm looking from the top, and I want to know how many atoms per centimeter squared, not centimeter cube, not volume, but how many per centimeter squared, then what would you do? Then you would say, okay, first define me the surface. So for example, if I look at the top surface, then I realize that the two surfaces, that each atom is now being shared by 4 neighboring squares, because I'm looking from the top, right? Not 8 as before. And in that case, the density will be 1/4 atoms per corner, right? It's being shared by, from the top, being shared by 4 neighbors, and 4 corners, of course. And the area is a squared, because it is a square on the top, looking from the top, area is a squared, and the answer would be, density will be a divided by a square, 1 divided by a square per centimeter square. Now, remember, this is called an areal density, not density. Areal density means surface density, number that you have per centimeter square. Now, this is, we'll come back to this later on in the course. Surfaces in semiconductors are extremely important, you see, because that controls not only the reaction rates as you deposit semiconductor, but remember the example I gave you, crystalline material and an amorphous material on top, how they line up will depend on, when two materials essentially built on top of each other, that will depend on how many surface atoms you have. So it's a very important concept. We should be able to count it. Now, what about if I had a different surface? Because remember, I can take a knife, let's say, and cut surfaces at any angle I want. So if I cut it along diagonal, body diagonal angle, then should my surface density remain the same? Of course not. And the reason it will not remain the same is that because although in each corner it's still 1/4, you know, these are rectangles, side by side rectangles, so there are 4 elements, so it's still 1/4 per corner, and there are still 4 corners, but you realize that since it's a body diagonal, so therefore the side length will be square root of 2 multiplied by a, right? It will not simply be a, and so therefore you can see on the bottom I have square root of 2a squared, square root of 2 multiplied by a, and that gives me a little bit larger area, and so the density is actually a little lower compared to before. And density determines everything, reaction rates, the flow of electrons on the surfaces. So therefore, this density on an inclined plane will be a little lower, and therefore the properties will be different. Okay, now let's talk about the other 2 lattices, body-centered cubic and face-centered cubic. Let's start with body-centered cubic. You can see that not only we have atoms on the corner, but we have one in the center as well in the body. And in that case, it should be easy to see that the number of atoms you have per unit box is 2, right? You can see 2 because there is 8 multiplied by 8 that's coming from the 8 corners that you have, and each corner is being shared by 8 neighbors, so no problem. What about that 1? Well, the 1 is the one that is sitting in the body, and that is not being shared with anybody. So I have 2, and the number of points per cell is 2 for body-centered cubic. Now, one thing you will realize in the body-centered cubic, let me step back a little, that if you look at the atoms, and if you wanted to calculate the packing density, you know, what fraction of the volume is occupied, then you should realize that along the diagonal, the atoms essentially touch each other. The sphere essentially touch each other, and from that you could calculate what fraction of the total space is being occupied by these atoms. What about face-centered cubic? Face-centered cubic has not only atoms on 8 corners, but there are 6 faces. And on each face, there is an atom sitting there. So in that case, how many atoms do I have? Well, I have 8 corners, 1 8 multiplied by 8. That's 1, just like the cubic one. But remember now, each surface is being shared by 2. 1 in the bottom, 1 in the top, 1 in the left, 1 in the right. So it's being shared by 2. So each atom is being cut by half in the middle. And so you have half multiplied by 6 faces. And so from the faces you get 3. From the corners you get 1. So you have 4 points per cell. That's clear? More or less? Okay. And again, in this case, if you wanted to calculate the packing density, you should realize that, look at the figure on the right, that the yellow, red, and the yellow one, that series along the face diagonal, that essentially touches each other. And so that gives you an idea how to calculate the packing density very easily. Now, these are very simple things, nothing complicated here, no reason to spend a lot of time. Okay, so remember, body-centered cubic, 2 atoms, face-centered cubics, 4 atoms per unit cell. Now, what about this hexagonal closed pack? Now, the hexagonal closed pack, what should be the answer? The first thing is, this is hexagonal, means that each face is in hexagonal shape, 6 atoms sitting on each face. On the top, I have 6. On the bottom face, I have 6. A total of 12, right? 12 atoms. You can easily count. So points per cell, let's see whether we can do the counting. First is, if you just think about the face and the one that is sitting in the bottom face and the top face, remember this is being shared by another corresponding column in the bottom. So each of these atoms will be cut in half inside the cylindrical hexagonal cylinder. So half per face, and there are 2 faces, so I have 1. Now, what about the other one? How many do I have on the ones that are being in the corner? Well, let's see. Let's see how it looks. So you will have another column like this, and let's focus on any atom. Let's say on the one where the red one is crossing. And so let's think about that atom. Do you see that if you looked from the top, then that atom in the corner will be shared among 3 such columns, 3 hexagonal columns, right? You can see it here, the 3 hexagonal columns. So inside each hexagon, then we have 1/3 of the atom sitting. But not really, because there is also one on the top and on the bottom. So you see, that is 1/3, of course, among the neighbors on the same plane, but between top and bottom, there's also another factor of half. And so that tells you that half between top and bottom, 1/3 become among the neighbors, and there are 12 corners. So what does it give you? 2, right? You multiply them, it gets 2. So how many atoms in the hexagon? Then I have 3 atoms per volume. For whatever this volume is, you can calculate. That will be the corresponding density of points per unit cell. So you should be able to calculate, for example, the packing density, the areal density, surface density, and all other things from here, right? These are general concepts should be easy to calculate. Okay. Now remember, these are all Bravais lattices. We haven't said anything about practical crystals yet. These are just geometrical constructs. And we'll see how to map things back to these type of structures in a minute. So let's talk about a few material systems and see how they translate back to the Bravais lattices. So one thing I wanted to point out, and that I had been saying just a few minutes ago, that we are talking about Bravais lattice, and I told you about the two definitions, equivalent definitions of Bravais lattices in the last class. But most material do not occur exactly in the Bravais lattice. For example, the one that you see in the right with yellow circle and green square, that of course is not Bravais lattice, is because the environment looking from the yellow atom and the one looking from the green square is not the same. It looks about the same, but from the yellow one looking to the right, you have a very close green neighbor. But for the green one looking to the right, you don't have a corresponding yellow neighbor. You have another one towards the left side, not on the right side. So it's not a Bravais lattice, and the way to transform this to Bravais lattice is to assume the green and the yellow together is an unit, and thereby transform it to one of the Bravais lattices. This we have done before. Now the point of this introducing this was to come to this point actually. So one is this rock salt lattice structure, and this occurs in a face-centered cubic lattice, as a face-centered cubic lattice. Do you see why? First of all, this is not a type of lattice we have seen before. Here we have sodium and chlorine. It looks like, if you just look at it, it looks like face-centered, right? But then you see there's another atom sitting in the body, in the middle. So is it face-centered or is it body-centered? In fact, it will turn out that if you look at this way, there's no unique definition. But if you do it this way, then it will work. Assume you pair a sodium and chlorine together, just like the yellow circle and the green square before in the last slide. You paired them together. When you paired them together and you replace them with one unit, geometrical point, and then you do it for everybody. So you push it up at one point, and let's take everybody and their neighbor and pair them up. So you can see the second one is sort of the bottom chlorine and smaller sodium. They have been pushed up. And you can see that you'll also pair up something from below, because that's where the chlorine atom was for that corner. And you do that for everyone, all the corners. Now do you realize that why this should be a face-centered lattice? That's clear, right? But you also realize this is a face-centered lattice with a basis, and basis is sodium chloride, right? Sodium and chlorine atoms together. Now you don't have to do it this way. What about, you could not only have to go, you can go in the vertical direction if you like, it's fine. You could go in the horizontal direction. So you could form basis in any way you wanted, and at the end, you will still get a face-centered cubic lattice, okay? But this is, of course, not a semiconductor, right? This is, sodium chloride is not a semiconductor, but there are more important semiconductors, which is a little bit more complicated, that we'll discuss next. The first one that I will discuss is this zinc blende structure for gallium arsenide. And you can see here the white atoms. Those are arsenic, and the bigger black atoms are gallium. And we want to know what to call this. Face-centered, body-centered, what should we call this? Again, we'll see that only if we transform it into a basis first, then look at the arrangement, we'll come to a conclusion. Now, I have given you the answer already. This is like an FCC lattice, but let's see how it comes about. So first of all, you can see there are 8 arsenic atoms in 8 corners. No problem, right? And you can also see that on 6 faces, there are 6 arsenic atoms. So that's also no problem. This is white. But where is this black one sitting? Inside the volume. That requires some thought. And let's think about it. In order to know where that one sits, this is how you should go about it. You should first find a corner atom on one of the arsenic corner atoms, and then go body diagonal on the other side. You see on the other side? That the blue one, rotating blue. And if you join through it a body diagonal, and 1/4 down the road, if you stop and place the black atoms there, that will be the position of the first black atom, right? What about the remaining 3 black atoms? There are 4 inside the volume. Well, you get the same idea. The first thing is identify the red atoms, and the red atoms have been constructed from the first red one. The other 3 has been because these are all neighboring faces. Face diagonal on neighboring faces. Do you see that? There, the first face, front face, you can see one on the top red, the side, right side face, and you can see the top right, the red, corresponding red one, and the bottom surface. You can see face diagonal on the bottom side is the red corresponding red one. And then from a given red, for example, look at the blue and the corresponding red. Again, you draw a body diagonal. 1/4 down the road, you put a black atom. And you do the same for all corners. This is how you create a zinc blende structure. Now, zinc blende and diamond structure that we'll discuss a little bit later, these are exactly the same, except that in zinc blende structure, you have 2 types of atoms, gallium and arsenide. If it had been one type of atom, then it would have been called a diamond structure. Now, how many atoms do I have per unit cell? By the way, none of these are primitive cells. In the homework, you will learn how to define primitive cells for this structure. This is not a primitive cell, but for this cell, how many? Well, you could easily see now that if you just look at the white ones, then this is face-centered cubic. And if you have face-centered cubic, then we already know 1/8 multiplied by 8, half multiplied by 6, because there are 6 faces, half of it on each face. And how much do you have the black atoms? You have 4 black atoms, so a total of 8. So that gives you a total of 8 atoms. And one thing people often talk about, that these are tetrahedrally bonded structures. And you can see why. The black atoms has essentially 4 arsenic atoms on them as neighbors, and that looks like a tetrahedra. This is like a triangular faces, this triangular pyramid, and so the tetrahedral structure it defines a zinc blende structure. Is it clear, more or less? Okay. Now, this is zinc blende structure. Now, what about, and for gallium arsenide it works, indium phosphide, remember the table we had? Gallium arsenide, indium phosphide, and there are many other materials that will work in zinc blende structure in semiconductors. Now, for diamond, a lattice for silicon, both silicon and germanium, these elemental structures from group 4 also occurs in diamond structure, or this tetrahedral structure. And you can see essentially these 2 are exactly the same in terms of structure and the same rules, but the ones that are sitting within the volume, again the same rules, 1/4 down the body diagonal, everything is the same, so you can do the calculation exactly the same way. Now, one thing you have to realize, that when things are within the volume in the body, there are 4 neighbors sort of tugging you along for every atom, and things are in equilibrium state and nice zinc blende structure occurs. But when you think about things on a surface, then of course things are a little bit more complicated, because you can see if you are looking on the top surface. Now there are these 3 gallium atoms, arsenic atoms on the top, shown marked by red, but the fourth one is down in the volume. So in one side you have air on the top, and on the bottom side you have a bunch of atoms. As a result, what will happen, and the top view is shown on the bottom left side, the big red atoms are the corresponding ones marked on the top with a red square. And what will happen, because the arrangement of the atoms on the surface is no longer symmetric, therefore, what will happen that on the surface of gallium arsenide, there will be this atomic rearrangements. I'm not going into the details of this, but there will be a rearrangement of the atoms, and as a result, surface of gallium arsenide or silicon are significantly more complicated than the bulk of the volume. But surface is very important, I told you, and we will get back to that later in the course. What about hexagonal close packed? This is cadmium sulfide. This requires some thought. This looks like a hexagonal except all those complicated atoms. So first let's think. So I have, just like an hexagonal, on the 6 corners I have 6 atoms, and also on the face, on the top face I have 1, just like before, right, in hexagonal 1. And then I have the corresponding sulfur atoms in their plane. So cadmium has their plane, sulfur has their plane. The same sulfur has in the same plane. I have similar 6 in the corner and 1 in the face, and also the same. So this plane, cadmium plane, will repeat. How many atoms here? Well, let's think. So if I'm looking on the top, and the black points I have shown here in green on this side, you can see that although my drawing is not exactly very good, but you can see the hexagonal. Looking from the top though, you can see the hexagonal, the ones that I have connected up, and you can see the face-centered one. So that is on that plane for the cadmium atoms. Now, the 3 cadmium atom that you see within the body, just below the sulfur surface, you can see, those occurs in the gap. Those 3 marked by blue, those occur in the gap of the original ones. So if you're looking from the top, you will find the ones that are in the body, those ones are occurring correspondingly here on the middle plane. And correspondingly, it will continue for the other surface. And in that case, how many atoms here do you have? Again, we have the same 1/6 multiplied by 12. Those are the surfaces, the corners that I have. And then half multiplied by 2. Where did that half multiplied by 2 come from? Top surface and a bottom surface. And what about that last 3? The 3 is sitting in the volume, shown here, marked here in blue. So that's all 6 atoms I have on cadmium, and I'll leave for you as an exercise to show that how to convert it into an hexagonal lattice. You'll have to do something to it, right? In order to convert it to a pure hexagonal lattice, form a basis, and then convert it. So I hope you'll be able to work it out. I'll get started on the Miller indices and continue in the next class. And so let's talk about, so I have talked about atoms, volumes, areal densities, surfaces, and all sorts of complicated things. But if you go home and read for an hour, these things will become clear. Let's talk about surfaces a little bit more. Now in semiconductor, as you saw, the atoms sit in various places, various corners and various places. And it's very important many times to define the surfaces. So for example, and the surfaces have names. And for example, the blue one on the left, they are giving 3 indices, 0, 0, 1, and saying that that's the name of that surface. The yellow one, they are saying 0, 1, 0. So every surface, you see, they have given a name. Now, how did the names come about? This is what the Miller indices are, and how the name come about is what I'm trying to explain, the naming convention of surfaces. Now, this is how it works. Assume that you have 3 atoms, any 3 you want, take 3 from the crystal. And you know from the three points, you can always pass a plane through it. So I pass a plane through it. What is this? What is the name of this surface? That's what I'm trying to calculate. So the first step would be to normalize the intercept. So for example, in the x-axis, you see I have the intercept of 2. Do you see that? On the y-axis, how many? 3. And in the z-axis, 1. So I have 2, 3, and 1. I'm giving you the algorithm, how the naming comes about. So I have 2, 3, and 1. Now you invert it. So 2 becomes half, 3 becomes 1/3, and 1 becomes 1. And then you rationalize it, right? So that the numerator becomes the same. And in that case, half becomes 3/6, 1/3 is 2/6, and 1 is 6/6. Take away the 6 from the numerator, and that's your surface name. 3, 2, and 6. That's your surface name, right? This is a Miller index for this surface. So this is as simple as this. So let's take some more examples. Think about, I have a surface where the plane, actually the atom is on the z-axis, but in the negative z-axis. What do I do about that? So I'll do the same procedure. 2 in the x-axis, 3 in the y-axis, but -2 in the z-axis. Not +2, -2 in the z-axis. Again, invert, half, 1/3, and -half, right? Rationalize, what will be? Half will become 3/6, right? 1/3 is 2/6, and half is again -half is -3/6. Take away the 6, 2, 3, 2, and instead of writing a -3, we'll take that minus and pull it on the top. And you can see that 3 has been pushed as a hat on top of 3. So the Miller index is 3, 2, 3 with a bar, right, for this surface. What about this surface? If it doesn't cut the z-axis at all, then what happens? Well, then you say the same thing. So the x-axis is 2, y 3, and then z-axis it doesn't cut at all. So probably it cuts at infinity. So 2, 3, and infinity. Invert it, half, 1/3, and 0, and then rationalize. Then it becomes 3/6, 2/6, and 0/6. Take away the 6, 3, 2, and 0, and that's the answer. Pretty simple, right? This is nothing in here. Now, one other thing people often use for hexagonal lattice, just for convenience, is something called a Brevet-Miller index. So Brevet has inserted his name there. But let's see how that works. So if you have a surface, which is shown here in that colored line, in the transparent colored line, and if you have 3 axes, but instead of x, y, and z, which are 90 degrees with each other, you have 4 axes here. 3 in the same plane, which is given by A1, A2, and A3, they are 120 degree apart. And the z-axis is the same z-axis before. So then, how would I describe this surface in this coordinate? This is how I'll do it. Do you see whether it makes sense? If you look at the A1 axis, the surface is such that if you extended it, it will never cut A1 in this particular case. So therefore, it cuts A1 at infinity, I'll say. So the first index on the top is infinity. What about A2? Well, it cuts A2 at 1, position 1. That's why it cuts it. A3? Well, A3 is going in that direction, but my surface is on the negative side, cutting it to the negative side. So I have -1. And what about the z-axis? Again, it's parallel to z-axis. So it will be cutting at infinity. Again, you invert it, 0, 1, -1, and 0, and you can very quickly check that Brevet-Miller index for this particular structure is 0, 1, 1 bar, and 0. And check that out. But one thing about this you should notice, if you haven't already, that if you have done your math correct during exam, this is a good way to check things. If you have done your math correct, then the first 3 must always sum to 0. This is, you can see 0, 1, -1. So 1 and -1 gives you 0. And no matter what surface it is, it will always be always be, this condition would be always be satisfied. But remember, for every Bravais-Miller indices, there is a corresponding Miller index, because it's a matter of putting axes and then getting the intercepts. So if you do it in a more complicated way, yes, conceptually it's easier when you're drawing a few diagrams, but you should always be able to convert it to Miller index if you needed to. Now I will show you that, I gave you an algorithm. How did they get this algorithm? I mean, is it something if I, dream up something on myself that this is a set of rules and give it my name, will it stick? Well, actually it will not stick, because this is a very good reason why this algorithm works. And this is how. Remember the first surface, 3, 2, 6? Where does this number come from? If you look at the vector R1 of the surface, do you agree that since the z-axis is along one intercept and x-axis has two intercepts, so therefore the vector connecting those 2 points is 1c minus 2a, a being the unit vector, right? What about the other one, R2? So R2y is the final point. There's 3 intercepts then I get a vector perpendicular from R1, and I take a cross product. I hope that you remember how to take cross product, but look at the answer, 3a plus 2b plus 6c. Do you see the correspondence between Miller index and these 3 numbers, 3, 2, and 6? So Miller index essentially is the vector, the integers that multiply the unit vectors for a vector perpendicular to the surface. That's where it comes from. So it's a poor man's vector algebra. That's what this is. If you don't want to learn vector algebra, then you can go it by this particular way. Now I will stop here, and I will, maybe I can continue on. There's 5 more minutes. So let me continue on. There's 2 more slides, and then we'll be done. If we wanted to calculate the angle between 2 planes, right? Many times you will see that's very important quantity. How will you do it? Now, if you remember from high school or maybe from college, how do you calculate the angle between 2 vectors? You take dot product, right? Not cross products, dot products you take. And if I have, first of all, a unit vector, this H1, K1, and L1 are the Miller indices for plane 1. And the unit vector for plane 2, H2, K2, and L2 are the Miller indices for plane 2. So if I simply take the dot product of these quantities, then that will give me the cosine theta. One thing people often forget is to normalize the vector. In the denominator, you need to normalize it, otherwise your cosine theta will not be between 0 and 1. It will become a large number. So you want to normalize it and thereby get the cosine theta, the angle between it. And one example is something like this. For example, if you wanted to calculate, so this is a silicon volume, and people will generally cut small wafers out of this. It's like cheese. So you take small wafers out of this. Now, there is something called a primary flat. These are historical things. The book is a little bit old. This is how it used to be. These days, of course, you don't have any of this primary and secondary flat. These days, the robot come in and there is this small notch. The robot knows, it doesn't require this type of visual cue. It knows which plane is which one with simple marking, and it can pick it up and do the processing. But for older days, this is how it used to be, a silicon volume, then you'll have to cut it at various angles. So for example, if the surface is 100, and if you wanted to know that 011, which direction is 011, then you could easily calculate the angle between them. So first of all, 100, that's the Miller index for the top surface. That means that's the vector, direction of the vector coming out of that surface, right? From the primary flat, if you say that that's 011, another vector. So if I multiply, take the dot product of these two vectors, I should be able to calculate the angle between them. And the angle between them is cosine theta. Do you see how it works? 1 multiplied by 0. So I'm taking the pairwise indices, the x index, the y index, and the z index, multiply them together. And what is the answer at the end? The answer for cosine theta is 0. Do you see that? 1 multiplied by 0 plus 0 multiplied by 1 and 0 multiplied by 1. So numerator is 0. Do you see where the denominator comes from? So square root of 1 is coming from 100. This is h1 squared, k1 squared, and l1 squared. So that gives you 1. And for the other vector is square root of 2. Do you see that? Because there are two 1s there on the vector. And from that, you can calculate the angle, which is 90 degree. Because cosine theta, when it's 0, the angle between them is 90 degree. So one is perpendicular to the other one. Now, one thing I was mentioning was that if you know the Miller indices and the information about these two other vectors, for example, in this case, one vector is coming perpendicular out of the surface of 100, that's one direction, and the other is perpendicular to the primary cut, which is 011. If you know these two vectors, then let's say your professor asks you to make a device along 0 to 1 direction because he believes that it will have interesting transport properties. You could easily solve that problem. And this is how you can see either on the left side, which is the top view of the wafer, or the right side, which is the perspective view, that I have drawn those two vectors, 100 perpendicular to 100 surface, and 011 shown here in red, perpendicular to the primary cut. Now, if you wanted to know, given these two vectors, where the third vector 0 to 1 would be, very easy, because you could easily calculate the angle theta 1, and the theta 1 is easily calculated by the dot product of the two vectors, and you know the Miller indices, so therefore you can calculate the dot product. In this particular case, the dot product turns out to be 0, and you can see why, because one of the Miller indices is 100, while the other one is 0 to 1. So at the end, when you multiply them out, you get 0, and therefore the angle is 90 degrees. So the angle between 100 and 0 to 1 is 90 degrees, and 0 to 1 will be lying on the surface of 100 plane. What about the second angle then? The second angle you will easily calculate with respect to 011 and 0 to 1, right? The second vector you have. And that you easily calculate. Again, you get an angle of 18 degrees, let's say for this case, 18.5 degrees. So you know the two angles with respect to the two vectors. So you uniquely determine the position of the blue vector, which is 0 to 1. Now, in this case, we were lucky that the vector turned out to be in the same plane as 0 to 1. If the angle was, let's say, 85 degrees or 120 degrees, then you would have to saw the wafer in an angle to define that 120 degree and then rotate it along. And so therefore, at the end, you will determine that 0 to 1 is in 18 degree with respect to the primary flat, and you will create your wafer or your device there shown here in the blue patch, and your advisor will be very happy. Now, let me conclude this lecture 2 by saying that we have tried to understand the periodicity of the lattice in order to really calculate the total number of atoms per unit volume. And if we can use this information about one unit cell, you talked about face-centered, body-centered, and other types of structures. From that information and from the information of the basis, then we can easily calculate that how many atoms do I have per centimeter cube of the material. So you may think we are done, we can go home, but that shouldn't be good in the beginning of the semester, because actually we are not done. The reason is, let's say I have just calculated the number of atoms per unit volume from the crystal structure, which is shown here in row. And from the periodic table, let's say for silicon, I want to calculate how many free electrons I have. I multiply it with number 14, because silicon has 14 electrons. So let's say, so in that case, if I multiply them out, then the total number of electrons is not really the number of electrons that is available for conduction. If you just multiply with the total number of electrons throughout, then you can see that the conductivity you will get for different material has no resemblance to anything that you measure experimentally. So what it means, that whatever number of electron a material has, well, while all those electrons are the same physically, but they do not all participate in the conduction process equally. A fraction of them do. And the whole purpose of the next lecture, and in fact next 3 lectures, would be to find what fraction of them is actually available for conduction. If you know the fraction, not the whole, only then we have an understanding about the transport property. And that requires an understanding of the quantum mechanics. And that's the purpose of next 3 lectures.